So let's go through the steps of vector addition using the component method with a given problem. In this problem it says Jamie walks 4 meters east and then 5 meters at 50 degrees north of west. So I'm going to skip between two pages here, but our first step will always be to draw. Okay, so let's draw our, it would be good if I switch to drawing here. Let's draw our problem. Step 1. Jamie walks 4 meters east. Okay, so that's along our x-axis. I'm a little off. Still slightly off, but that's okay. 4 meters east, and then 5 meters at 50 degrees north of west. So, just so we know, 50 degrees north of west is going to be in this direction from the origin out this way. And I'm not using a protractor, but I'm just sort of guesstimating to have an idea. Alright, so that's just sort of an idea, and I'm hoping that my resultant vector is something like that. So I have an idea of where I'm going now. Now I need to separate the vectors and determine the angle of the vector relative to the positive x-axis counterclockwise. So let's look at each of our vectors. My first vector is 4 meters east. The angle relative to the positive x-axis in this case is going to be 0 degrees because it is on the positive x-axis if we are going east. My second angle, it might be easy to draw a coordinate plane. My second angle looks like this, and it's 5 meters. Now that's 5 meters north of west, so we start at west and we sort of go up 50 degrees more than that. But I want this angle from the positive x-axis going counterclockwise. So if I know that this is 50 degrees, I know that my angle theta in this case is going to be 180 degrees minus 50 degrees, which is 130 degrees. Okay, so I have done step 2, where I've separated my vectors and determined the angle of the vector relative to the positive x-axis counterclockwise. Now, next step is I'm going to determine the x and y component vectors for each of my individual vectors. And this is where some of our equations from the last video come in. We determined with our equations that we can find the x component vector by taking the magnitude of our original vector times cosine theta. And we can find the y component vector by taking the magnitude times sine theta. And what I like to do is I like to set up a little table. Okay? So I like to set up a table that has the magnitude of my original vector, the theta of my original vector, its x component, and its y component. Okay? So I have two vectors here. Now, the magnitude of my first vector is 4 meters, and the theta is 0. The magnitude of my second vector is 5 meters, and the theta is 130. You know what, I'm going to do those in a different color so it'll be easier. And I can do the math on my calculator. But for example, just so we know, I'm doing, to do this, I'm doing 4 times cosine of 0 degrees. And you have to make sure that your calculator is in degrees and not radians. Okay? It turns out that the answer here is 4. For this, I'm doing 4 times the sine of 0 degrees. That turns out to be 0. Now, this is a nice place to check our work. Look at the values for the x and y component vectors and what our vector looks like. Does it make sense that we're going 4 in the x direction, in the positive x direction, because it's positive 4, and 0 in the y direction? It does, because this vector is on the x-axis, so it makes sense that it's positive in the x direction, nothing in the y. So these work really well for us. Let's move on to this one. So here I'm doing 5 times cosine of 130 degrees, which gets me negative 3.2. We'll just take it to that many decimal places. And for my y, I'm doing 5 times sine. (130 degrees). Which gets me about 3.8. Now, again, let's check to make sure that this makes sense. This is telling me that this vector is going negative 3.2 in the x direction. And that makes sense. We are going in the negative x direction with this vector. This is telling me that I'm going positive 3.8 in the y direction. That makes sense again. I'm going positive in the y direction. And also just, again, this was an estimate, but looking at this vector, it does sort of make sense that our y is slightly greater than our x. So that's great. We finished step number 3, determining the x and y component vectors. Now, we move on to step number 4, finding those for our resultant vector. And the way that we do that is we're actually going to take the sum. So for our resultant vector in the x direction, that's going to be the sum of the x component vectors for all of our vectors. And so on. If we had a bunch of vectors, for the y vector, it would be the same, a sub y, b sub y, c sub y, etc. On our table, this is easy. We can just add together 4 plus negative 3.2 is 0.8. 0 plus 3.8 is 3.8. Perfect. Now we can do Pythagorean theorem, where we are doing solving for our overall vector Alright, or we can rework this to be our component vector is the square root of our x squared plus our y squared. So we can do that over here. We can solve for a component vector with the square root of 0.8 squared plus 3.8 squared. And by the way, again, we can check our work here. Notice our estimate, right? Does it make sense that we're just slightly into the positive x and really high up in our y? Yes. So it looks like our drawing was leading us to the right way. So if I do this math, 0.8 squared plus 3.8 squared under a radical, I get an r value of 3.8, so I'm going to make this 3.9 meters. And that seems to make sense overall. Now we need to find the theta, and in our last video we talked about how you can do theta is going to be equal to the inverse tangent of the r sub y over the r sub x. So here we can have our theta equal to the inverse tangent of r sub y over r sub x. Again, your calculator should be in degrees this entire time.
Hello.
And you get a theta of 78 degrees. And so now we know that we went 3.9 meters at an angle of 78 degrees.